Hello, I'm coming at you from the future. So before we start on this lecture, and we'll talk about many things, I just want to give you a heads up as to where we're going and why I'm showing you all this stuff, because towards the end of this first lecture 3, I'll be giving you a bunch of libraries and we'll talk about all the stuff that's there, and I will write these things. I'm from the future, remember. And I just don't want you to get overwhelmed. And remember that this class is not about memorizing anything. I just want you to have seen all this stuff before we do fancier examples. And even in lecture 4, I'm going to give a bunch of little examples. And this week we won't get to the bigger ones, but that's where we're headed. So I just want to give you a sneak preview so that you understand that it's not about memorizing. It's just that I have to get you up to speed with some initial information so that we can start doing cooler things. Alright, so this is like a standard example that you may have seen before. We'll calculate grades based on the user, and guess the number is kind of my favorite thing to implement for these initial lectures. So look forward to that, but that will be happening next week. Okay, so that's where we're going, and so I'm just going to give you a lot of information in these lectures to get you there. And don't worry about memorizing these things, because always you can come back, look at these slides, look at the documentation online that I'm going to show you. Yeah, don't feel overwhelmed. This is just so that you've seen this before. All right, I'm not going to make you memorize this stuff. All right, hello and welcome to your second week. We're on these slides with all these words, and we stopped last time right about here. So let us continue. So how much stuff can you put in a type? We have a bunch of different types that we've talked about so far, and here are some of the number types that exist in C++. Int, char, and double we talked about. There are some others with fancier sizes, but these are the standard 3 that we'll be using in this class. And those have an associated size. So I do draw ints like a box. If I say like int x, well, now x is a box, but it's not an infinite box. It's not super big. It's exactly 4 bytes. And you can't put any more or any less in there. Every int that you make is always going to be 4 bytes long. And that means that you can't write every integer under the sun. You can only store ints from -2 to the 31 to positive 2 to the 31 minus 1. I think the representation of negative numbers is beyond the scope of this class, but come to office hours if you're interested in knowing why. But there's a 32 in here, and I want to show that to you. Okay? And then characters, they're pretty small. They can only hold 256 different things. And then doubles are twice the size of ints, and we're going to talk about all this in just a second. Doubles are twice the size, and they can hold decimal values with 16 digits of precision between some very large numbers. Okay? And then you have these other options that you can look into. If you need more room in your ints, you can use a long. But, well, I'm talking about bytes. How does that imply these ranges? And what is a byte, you might ask? Well, I'm glad you did. So let me teach you now base conversion, and in particular, we're going to go from binary to decimal and vice versa. All right, so we have a bunch of different terms that we'll talk about, and let's get started. So it's probably easier for me to type right now, so I'm going to do that. So our numbers that we know and love are in base 10, we say. Okay, and that's because we have 10 different digits. Oops. We use 0, 1, all the way to 9. Okay? And so that's 10 total digits. And the second we run out of space, we have to make a new place. So you can go all the way 8, 9, but now I've run out of digits, so I have to add another place. Now we start at 10, right? So binary, oh, by the way, the idea is, why did we come up with base 10? the main theory is it has to do with the number of fingers that we have in total. And so maybe if you lived in the Simpsons world, they would be counting in base 8. All right, so now that we know what a base is, it's pretty easy to define every other base. Binary is base 2. So just by telling you that, you know already that there are only 2 digits we can work with. It's always, it doesn't go up to 2, it's 0 and then 1, right? And so once we're out of digits, we have to go another decimal place. So 0, then 1 looks like that, but now we're out of digits, so 1, 0, this is equivalent to our 2, okay? This is really 2 in base 10. And the way that we differentiate between numbers, because 0 and 1 is definitely part of decimal, how do I know if this number is binary or decimal? You can specify by putting the base at the bottom in a subscript. So this is the decimal 10. And this is the binary 2. All right? That's the idea. So base is binary. And a single binary digit, so these are decimal digits, these are binary digits. People wanted to be clever, and so they took that letter and squished it next to those 2. And so instead of binary digit, we say bit. All right? So it's just the number of digits in a number that is in binary. So this is a 2-bit number. That's the idea. And then a byte is just a collection of 8 bits. Maybe I'll say it like this. A byte is 8 bits. Okay? So in a byte, you have these possibilities. You can go 4 zeros, and then all the way down to 1, 1, 1, 1, 1, 1, 1, 1. Okay, that is a lot. How do we know which numbers these are? How do we convert? Okay, so if you remember from, I don't know, elementary school probably, do you remember how to break down decimal numbers into their places, like the hundreds place, the thousands place? Do you remember writing that out? Well, this is actually going to come in handy for once. So we know that this is equivalent to 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 4. Okay, and this, when we talk about powers, it's always going to be in terms of the base. So that's maybe a little too early for me to say that. But how about this? Look what happens now. So 1,000, what is 1,000 but 10 to the 3? What is 100 but 10 to the 2? What is 10 but 10 to the 1? And what is this times 1 but 10 to the 0? Okay? With that, how do you convert this binary number to decimal? Well, it's not too bad. You start backwards. It makes more sense to do that and work this way. So we'll take that 0 at the very end, this one right here I'm working on. And so it's going to be 0 times 2 now, because it's always the base. Okay? We're multiplying times some power of our base. And we start at 0. So that very rightmost thing can be either a 0 or a 1, and that represents the digit 0 or 1. So it's times 2 to the 0 for this number. Technically, we didn't have to include it, right? It doesn't add anything. Then this digit, it's going to be plus 1 times 2 to the 1. Okay? And then this digit is 0. 0 times 2 squared. And then this digit is the 2 to the thirds place. 0 times 2 to the 3. And then finally, 0, 1, 2, 3, 4. We have the 1 times 2 to the 4. Okay, and so that is how we convert between binary and decimal. All right, so 2 to the 4 is 2, 4, 8, 16 plus 2. And so this number was really 18 in decimal. Okay, and so now you can do this for any number. Just remember to start at 2 to the 0. It's always a power of that base. All right, now try this one. Maybe pause the video, try it on your own. Because this is how you know. This is like a 4-bit number, the largest one there could ever be. This will tell you why int has these max sizes. All right, or you'll get close to the idea. We don't want to talk about negatives yet. So this, working from right to left, remember, it's 1 times 2 to the 0, plus 1 times 2 to the 1, plus 1 times 2 squared, plus 1 times 2 to the 3rd. So that is, this is the 8th place, plus 4, plus 2, plus 1. Okay, so that's going to be 15 base 10. Okay, I hope that's not too bad. So that's binary to decimal. Fun stuff. The other way is a bit harder. So I'm going to teach you this algorithm, which is a recipe, a sequence of steps to take a decimal number and convert it to binary now, because that's how it's going to be stored inside of your computer. It's important that you know that. So now you know what it's going to look like. All right, so I have this base 10 number, and I want to convert it to binary. So first of all, let's make a simpler algorithm that just gets all of the digits out of this number. All right, so that's what I want. I want to extract the digits, the decimal digits, from this number, 1,234. And maybe take a second, think of how you might do it. What operations could you do to get these digits out of this number? Okay. Well, if I wanted this 4, there's one way that we can do it, and that brings me to an operator in C++ that you might have read about in your book so far, but maybe not. So let me write some code just briefly. Okay, so I want to go to my Windows desktop, code from class, CSCI 40, and this is going to be lecture 3. So I'm going to make a new directory, make a new folder in this folder called lecture 3. Go into it, and let's talk about remainders, or modulo, because that's the name of the operator I'm going to show you. All right, so there is a corresponding thing to division that you may have heard of, the remainder. So it's especially helpful for integer division. So here are my two numbers, int x equals 42, int y equals 5. I can divide x by y and get some number. It's going to chop off the decimal places. But if I want to know how much was left over, how many things out of 5, it's going to be 0 through 4. Those are my possible remainders. I can do this. This is 42 divided by 5. Integer division is whatever this is. Now, let me show you this. 42 divided by 5 remainder is this operator. So you replace the slash with a % sign, and that's called the modulus operator. So it's like we're converting, we say 42 modulo 5. It's like the verb form. Okay, so that is that. And yeah, let me show you that in action, because that is the missing piece of our puzzle right now. So let me go to Windows Desktop, code from class, CSCI 40, lecture 3. Let's compile and run this. G++, standard equals C++ 17, modulo, -o modulo. And I forgot to spell, I spelled namespace wrong. Maybe you've been yelling at me through the screen. Sorry about that. And now everything's normal. So it looks like 42 divided by 5 is 8, remainder 2. Okay? And that makes sense because it goes in cleanly to 40, and then it's got 2 left over. Okay? So this is how you get the remainder out of an integer division operation. Okay? So that's called the modulus operator, or in action it's called modulo. Okay? Well, with that in mind, how do you think you might extract this 4 from 1, 2, 3, 4? And assuming you've thought about it, perhaps you came up with this idea. 1, 2, 3, 4 mod 10. Mod is even shorter for modulo. I'll call that mod. Is equal to that 4. Ooh, that's nice. I just got 1 digit out. Now, maybe if I could keep doing this kind of process, this whole mod by 10, I could get the other digits too. So how do I convert then 1,234 to 1, 2, 3? Because then I could do the same operation to get the 3 out. How can I do this? And then, let me show you. We just did 1, 2, 3, 4 mod 10. If I wanted to get rid of this 4, what could I do in integer land? Maybe I could try to make that number, because then it would go away, that 4, by integer division. How about that? Oh, that's exactly what we wanted. Mod 10 divide by 10. Integer divide by 10. Okay, so that's 1, 2, 3, 4. Integer divide by 10. Suddenly I chopped off this last digit. And then I can do mod 10 again to get the 3. And then I could do 123 divided by 10 to chop off. This is integer division. To chop off the 3 to get the 12. Then I can do 12 mod 10 to get the 2. And then I can do 12 integer divide by 10 to get the 1. Then I can do 1 mod 10. Doesn't go in at all, just leaves that 1 left over. And then I can finally do, at the very bottom, 1 divide by 10, and that is 0. And that is our stopping condition of this algorithm. I am done, and every time I took a remainder, I extracted a digit. That one, that one, that one, and that one. I got them in the reverse order. With this idea, we can extract the digits in binary form too, because the idea is that we're always moduloing, we're always dividing, getting the remainder by the base. Do you see that? We're also dividing by the base. So if I wanted to convert 1, 2, 3, 4 in decimal to binary, how about I extract the binary digits of that by doing mod 2, integer divide by 2. So here's the algorithm that we came up with. It involves repeatedly dividing and taking the modulus by the base we're trying to convert to. So let us give an example now of converting, say, 15 base 10 to something base 2, and we know the answer. We're just going to check that our algorithm makes sense. So the first step is to extract the rightmost bit from 15. And so instead of 15 mod 10, we're going to mod by 2, which is the base we're trying to get into. So this is an odd number. It's going to be 1. And that's helpful because we know that this is now the rightmost bit. And because we know the real answer, we're on the right track. Okay? And now it's as if we need to shift right away from that rightmost bit. We need to get rid of this 1 from 15 somehow. And the way you do that is say 15 integer divide by 2. So that's 7.5. So drop the decimal places. It's going to be 7. And now we're working with 7. It's as if 15, if you get rid of this 1 in binary, you're left with 7. And that's exactly the case. Okay? So 7 now mod 2. Again, it's an odd number, it's 1. And now we're going to shift away that 1 out of the 7 so that we can calculate the next few bits of it. Alright, then we'll say 7 integer divided by 2, 3.5, so it's going to be 3. 3 mod 2, it's odd again, so it's 1. And then 3 integer divided by 2, it's 1.5, so 1. And then we have 1 mod 2 is 1. And then finally 1 integer divided by 2 is 0, and that is our stopping condition. We're all done. And so we calculated the bits of this number in binary, in reverse, every time we took a modulus. Every time we took the remainder. So there's 1, there's 1, there's 1, there's 1, and we read it backwards. So the number that we calculated is, well, it just so happens that it is 1111 base 2, and you can always check yourself by converting this back to decimal, because that's the easier way to do it. You say 1 times 2 to the 3 plus 1 times 2 to the 2, and so on. So that is a quick introduction to binary. You'll read about it more in your book, but this just gives you some more intuition about what things look like in memory, I think, and I hope that's a little bit helpful. And so now you can understand at least part of this table. You can understand why character, maybe not why it's holding negatives, but why it can only hold 256 negatives, because it's holding just one single byte. So that's how many things you can store in 8 bits, because 1 byte is 8 bits. And so, for example, again, 4 bytes in an int is really a 32-bit number. Okay, and so there's a bit of an interplay there. It's almost 32. And so the one odd person out is double. They store their numbers in a very interesting way. And yeah, come to office hours if you want to learn more about doubles. I think that's all I wanted to talk about. Let's get back to programming now. So one thing that will come up probably later and become more important is this idea of a constant. We know how to make variables, and we can actually go and change those variables by saying, I don't know, int x equals 42, then you can say x plus plus, or x equals 47. And all these things are going to change that original x, okay? Maybe that x was not meant to be changed, and it was more of a mathematical kind of thing. You can put const in front of that declaration to ensure that your variable never changes. All right, so let's do that. So I'm going to make a new file called const. Here I am. Actually, let me copy most of this. Save me some typing. All right, so now I'm back in my const.cpp. You can see at the bottom. Let me make double pi equals 3.14159265535. And then maybe I'm having a bad day. I'll just say, no, pi is really 3. That should never be allowed to happen, right? Well, it compiles. It's allowed. We can print out pi. And we made it 3. No, we don't want to do that ever. So, oops. What you can do is put const at the front. And now this will not even compile. Okay, so watch me try and compile it. It's going to say assignment of read-only variable. That's the key. That's super nice. We can no longer change pi after it's declared. And by virtue of being const, you have to immediately give it a definition too. You can't just say, all right, I have this constant, and I'm going to define it later. No, you got to give the value up front. Whee. Dun, dun, dun. That's a bad idea, because you can never reset it. That's the idea. So that's not allowed. and now we're all fine. So what do I want to put above this? How about this? The compiler will not even allow the following line to exist. Well, it's not a runtime error, it's a compile time error to try and change a constant. Okay, so that is a const. Use that as much as you can. That's very helpful when debugging. Alright, so let us move on now to function calls, because I am about to show you a bunch of different libraries, and inside of those libraries are functions, these things called functions that you can call. It's an interesting kind of metaphor. It's like you're talking to somebody, I guess, and they're doing something for you. So a function is a piece of code that you can call multiple times. Every time you call it, it runs. Okay, so you can tell it to do its thing by calling it. All right, and so every function, it has a name, and then it has some arguments. Sometimes it has 0, sometimes it has multiple, and those arguments kind of tell it what to do. So you can control the function with the arguments. All right. Alright, so that is a function in a sense, and the syntax is probably the weirdest thing. It's you say the name of the function first, then you have an opening parenthesis, and then in between you have as many arguments as are necessary, and then you have a closing parenthesis. And this entire thing is called a function call. Okay? Maybe I'll put this in a different color. It's called, well, it's a beautiful thing, so it's a function call. It's wonderful. And what's going to happen is it will be replaced with the result. Okay? So you can think that this function call will get replaced with the result. Whatever this function was supposed to do, its answer that it gives back will be replaced with it. So functions usually give back an answer, and you can pretend that your function call will be replaced with that answer. Alright, so that's a very important concept, and I'm going to give you plenty of examples on the next 3 slides, so don't worry too much, but here are some examples of function calls. So in the math library, for example, there's a function called square root that gives you back the square root of a number, and this is how you would call it. Square root, open parenthesis, 2. And that would give back whatever the square root of 2 is, like 1.71 whatever, right? Maybe not, but that's a square root function. There's also a random number generation function that just gives you back a random number with no arguments required, so it would give you back, like, I don't know, 1,284, that's its random number that it's giving to you. And then there's ones with extra things, like, for example, pow. That's the power function. You can give it, like, 2.5 and 3.5, and that'll give back to you the result 2.5 to the 3.5. Okay, it'll calculate that for you and give you back that double answer. Okay, so there's always some functions that take arguments, and those arguments are of a certain type. So this has a type 1, this has a type 2, and the result of the function also has a certain type as well. Okay, so we'll talk about that. That's all. So now let's get into math functions, and I am linking to a page where I think you will spend a lot of time this semester. It's the documentation for individual libraries. So now we have some new ones that we're going to talk about. This first one is CMath. So it's the math library from the C language, which happened before C++. And if you ever want to look at more things or get to this page easier, you can always just search Google for C++ and then the name of the header that you're trying to look at. So it's usually the first thing. And then here is the list of all of the things that the CMath library gives to you. And there are many, many, many. Also notice that several of these things, like the round function, which is nice to have because it rounds a number, are only available as of C++ version 2011. So that's why we're using the cool new stuff, because the libraries get updated. They're helpful. Okay, there's the pow function, square root function. Let me show you these in action. Okay. Oops, I don't want to save that. I want to make a new file, math.cpp. Okay. That's our boilerplate, but now we're going to include the CMath library for the math functions. Okay, and so now you can just use it. You can call these functions and use them as you would expect. So let's pretend that we want to use the cosine function. Let's get the cosine of 0, for example. So we can just print it out, pretend that a function call gets replaced with its number. So cosine of a 0, I guess. And then a new line, so cosine of 0 is a function call. It'll get replaced with its answer. Okay, so let's compile and run this so it prints out. Oops. And it prints out 1. Very, very nice. So how did we know all these things? So if you click on each function, it tells you more about it, and it also gives a nice, cute little example, which is nice, and it tells you exactly what it does in English, and it also tells you the kinds of types that it's expecting and that it gives back. So here is one option for the cosine function, and we'll just focus on that one. Don't worry if this syntax doesn't make a whole lot of sense to you right now. It will become more, it will make more sense later, is what I'm trying to say. So this is the cosine function. It has one argument called, inside of itself it calls it x. We don't care about that. We just know that it takes one argument and it's a double. And it gives us back a double answer. Okay? That's the idea. So that's the cosine function. Not too bad, not too bad. And I don't see pi here, so if you wanted pi, you can do the inverse tangent, the arctan of 1 times 4, right? If we wanted pi, cout atan 1 times 4, and these are function calls. What do we want cosine of? We put it between those parentheses. Okay? What do we want to the inverse tangent of? We put it between those parentheses. Okay, now we have pi. There. Moving on, the exp function does computes e to the something. So exp of some value, one value, gives back a double that is e to that value. So if I wanted e, if I wanted the value e, I could do exp of 1, right? Because that'll give back e to the 1, which is that constant e. That's useful sometimes. So we can say, oops, we could say exp of 1. So these are pretty similar. These are one argument functions at the moment. And there's our e. Dun dun dun. All right, let's keep going. Pow and square root, those are nice and useful. So pow is, it takes 2 arguments this time. The first thing is the base, and the second thing is the exponent, and it returns you back a double that is base to the power of exponent. Okay, so it's cute, and it's saying it right there. So let's calculate, I don't know, 2.5 squared. We'll say pow, 2.5, that's the first number, and the thing that we want it to the power of comes next. And now we're good to go. This will compute 2.5 to the 2. And remember that this caret doesn't exist the way you think it does in C++. If you said exactly this to C++, it would give you a weird thing. I don't even know if it works with doubles, actually. It's not power. You have to use the pow function. Okay, so 6.25 is the answer there. And then square root takes one argument, a double, gives you back a double answer that is the square root of that argument. Okay? So these are weird words like argument, call, but I promise you'll get used to them. It's just how people decided to talk. Where was I going? Square root. Very nice, very nice. So yeah, these will come in handy very, very much. And I think before I bore you too long, I'll show you seal and floor, and then we'll do round, because round is important for your lab. So I don't actually have to give you floor and ceiling, but it's what these two functions do is they round up a double or they round down a double. So it'll always go to the next whole number or the next higher whole number or the next lower whole number. So for example, if you had 2.15 and you gave that to the ceiling function, or I'm about to show you the result of seal of 2.15. I'm going to draw it like this. So if you use the ceiling functions, like it's up here, and then there's the floor down there. That's the idea. Seal would give it back, would give you back the 3, and then floor, the floor function, would give you back the next smaller whole number, so it would give you back 2. Okay, and so now I'm going to show you round, which is more useful. You'll need this in your lab. So rounds to the nearest whole number. So takes a double, gives you back a double. That is a result of rounding things. So you can say round 2.15 would round to 2, and then 2.5 though would round up to 3. That's the rounding you know from math. Okay, so we get back 2 and we get back 3. And so in your lab, you're going to round to the nearest tenth instead of the nearest whole number. So you'll have to figure out how to use this function to do that. Yeah, I think that's everything that I wanted to say here. There are abs and f-abs, which in essence have the same types and do pretty much the same thing. This returns the absolute value of a number, and there's also a version of that in cstdlib that I'll show you now. Okay. So cstdlib is also in the C library. It's down here on the left side. Click that and see what's there. I'll talk about random on the next slide. I think I want to talk about exit, and then also just abs briefly maybe. So abs is for absolute value, and if you want a double absolute value, you can use the CMath version of abs, but the same function is defined in cstdlib, and it gives you the int version. So it takes an int and gives you back the absolute value of that int. Okay? So let's give an example of that. And it knows which one I'm asking for based on the type. If I gave it a double, it'll use the CMath version that took the double. If I give it an int, it'll use the int version from cstdlib, or C standard library. So abs -42 versus -42.5. Okay, so that's that. And then there is this function called exit that I want to show you that just stops the program. You can call it from anywhere. When we write our own functions, it'll be useful because returning from main stops the program, but returning from another function does not do that. So there's this helpful exit function that is the same as stopping your program with a given status code. So let's say I hate the program, I'm done with it. I can say exit, and then a status code, and it will stop the program. So it'll never print out these last 4 lines if I use exit. Okay, you see how it got cut off? And now it's happy again. So exit will stop the program from wherever you are in your program. You could also equivalently, inside of main, return the status code. That'll also stop the program. All right, yeah, I think that's everything that I wanted to show you from here. Just feel free to explore. Now, random numbers I am excited about. They are very fun, and I'll give some demos, but the idea is there's a function. It's called rand. It exists in cstdlib, and it gives you back a random number. So let's talk about these things. I'll make a new file called rand.cpp, and I will include most of this. Boop. And then we're going to call rand. Give us back a random number, please. Okay. So back to this. Click on it. It's like generates a pseudo-random number, and we'll talk about what that means in a second. It gives you back a number between 0 and a special large value called rand max. But let's see it running. Dun dun dun. I'm excited. We're going to get a random number printed out to us. There's our random number. Okay, so I run it again. That's possible. That could happen. It's very unlikely, but two random numbers could be the same, one after another. Let's try running it again. Oh. I think there might be a problem. So the problem, after I say this, rand gives you back a number between 0 and this special large number called rand max. Okay? But the caveat is rand needs to be seeded so that it produces a different random number each time. So that is the issue. You just have to give it a special starting point, and then it'll start producing actual random numbers for you. Otherwise, it'll always give you the same sequence, because that's what rand has inside of its head. It's producing a certain sequence of random numbers, and it knows where to start, and it knows how to get the next one. There's the next one in the sequence, like, I don't know, 84, 97. And so if it's here, it knows that the next random number is here, but we want to start it off in a random place. That's the idea. So we're going to do this thing called seeding the random number generator. Okay, so that is why there's this special matching function called srand. Okay, that's all. So we initialize the random number generator with this srand function, and we give it a starting point that it can start its randomness from. Okay, so that's what srand is for. And we usually give that a nice number that always is different. That happens to be the current time. So that's where we want it to start its randomness from, the current time. And so there's this time function in the time library, the ctime library. The current time, which is really the number of seconds since January 1st, 1970 at midnight. But we don't need to get into that. I'm just going to show you how this works. So this might be the one thing that if you want to use random numbers, you got to remember to do this. Seed that random number generator with the current time. I'll give it like this. Seed the random number generator with the current time. Okay. And now, every time I run this, we'll get a different value between 0 and that rand max. Okay? Run it. Hey, this is nice. This is nice. We're getting different values. They're very large, though. And if you run it fast enough and the time hasn't changed, you'll get the same value. All right. That's useful. But that's a lot. Like, these numbers are huge. Usually we want like a number between 0 and 100, right? Something like that. That would be really nice. Pause the video for a second and think how you could use some math things to get you to go from a very large number between these things to a smaller range. Okay, now that you're back, maybe you decided on something that we talked about earlier. you can do rand modulo some number, and that will always give you back a value between 0 and that number minus 1. Yeah. Okay, that's useful. That's what the remainder is. It's a number between the thing you're dividing, between 0 and 1 less than the thing you're dividing by. Okay, so that's useful because we can say now rand mod 100 to get a random number between 0 and what? That's right, 99. So get a random number between 0 and 99, so a random 2-digit number, potentially 2-digit number. So that's a bit better. So now we can do cool stuff with this. In any game like that has enemies moving around that's different every time, it's using some kind of randomness inside of its code. So this is very useful, this concept of randomness. All right, so here are my demos. We're going to output 3 random characters. So let's do that. So let's pick 3 random characters. So rand will give us a number between something and a large value, 0 and a large value. We want to shrink that down into the size or the values that characters can be, which are technically negative 127 to positive, negative 128 to positive 127, but let's just deal with positive numbers right now. So if we want a number between 0 and 127, we're going to mod by 128. And right now, this will just give us back a number. But we want it to print it out in character form, so how do we convert? Do we remember? It is static underscore cast and the type we want. So we want to make a number from a character. And so this will now make it all work. And we'll get 1 random character, which is sometimes non-printable. Oops, didn't want to recompile. So now we can get printable characters if we're lucky. So we'll do that 3 times, see if we get any fun words out of the mix. Oli, nice, nice. We got some nothing there. Looks like one of those was a new line, which is exciting. The character for 0, 4 times I. Fun stuff. So you can invent the works of Shakespeare randomly, of course. Now, another thing. Oops. Let us get a random number between 1 and whatever the user wants. So if rand mod num gives us a random number between 0 and num minus 1, how can we use that to get a value between 1 and num? So I want to go between, I had 0 and num as my range, but I want to somehow turn this into 0 and 1, num minus 1. I want to turn this into a range between 1 and num. How can I do that? Think about that for a second, maybe. And the answer is adding 1, because 0 plus 1 will give me back the starting value of 1. That's the smallest thing. And then the largest thing I can get by adding that, num minus 1 and 1, is num. So then my range will be correct. So I just need to add 1 to this, and I will have the range that I wanted. Okay? So now I'll ask the user, enter a max value, get it, now we have it. Let's output a random number now. See out. So rand mod that maximum value that the user wanted, and we're going to give back. So right now this is between 0 and max val minus 1, but we wanted a value between 1 and max val. So we'll add 1, and that's all. Max value 100, get 85. Max value 2, we get 1. Okay, that's useful. Oops. So those are random numbers. They will be very fun and exciting. And now let's move on to strings. So the string library. This lives in string. Alright, so I'm going to make a new file called strings.cpp, let's say, and copy the boilerplate, of course, as one does. Oops. Don't really need any of these, but we do need string, so. Oops. Okay, so let's now go to the string library on the internet. So that just so happens to be, it's good to know how to move around this website. String happens to be an other. Go here, string, and you can click the string type. And here's all the things you can do to a string. And ones that you'll probably care about are, we know how to get the character at a certain index. Wouldn't it be nice if we also knew the length of that string that we were given? Okay, so you can use size to get the length of a string. Okay? There's also length that's equivalent. And you can click it so that you know more about it, of course. That's how it works. But what's interesting about these functions is they operate on strings in a different way. So here's my string. If I wanted the size of this string, I don't say size s. I'll actually say this, s.size. This is a different kind of function. It's called a method. It acts on s itself, we can think of. But that's how you use these functions for strings. They're different. They're part of something called a class. So we'll talk about that later. But this is what you need to know. String functions, they belong to the string itself, in essence. So now I'll output the size of our string. Alright, the size was 5. Yeah, that makes sense. There's 5 characters. Now, let's talk about the plus function. And so strings aren't numbers, of course, but you can add two strings together. You have s1 plus s2. That'll actually give back s1 and then s2. So if s1 was hi and s2 was mom, this would give back the string hi mom. And you could have put a space in between if you wanted to. Okay, so it kind of adds them together. That's what's called concatenation. See out. So I'll put a space. There we go. That's pretty self-explanatory, I think. So there's a plus function. Well, it really is a function, but there's a plus operator that works on strings too. And now let's get to these, because these are a bit more interesting and maybe complicated. But again, I'm not asking you to memorize these things. I just want you to have seen them. So let's talk about some string find. Where did that go? When in doubt, Control F. So you can search for a character inside of a string. You can also search for a string inside of a string. Okay? And this is pretty complicated how it's saying you can use it, but I'm just going to show you examples, and it might be easier to just look at the examples for these that I'm going to talk about. So find finds the first occurrence of a char/string inside a string. Okay, that is the idea, and it's, remember, it's like s.find, and then you give either the character that you're looking for, or else you could also give it a string. And it'll give you back the location, the index of that char/string. Okay, so for example, here is my string s is apple. Yeah. So on my output, where is the L in apple? S.find that character L for me, please. So this will give me back the index of the first L in the string. And so if you were to search for P, it would give you back the first P's location. So it looks like this happens at index 3. That's where the L is. And remember, your indices, here's my string S. It looks like this in memory. It's got an A, P, P, L, and an E. And this is index 0, 1, 2, 3, 4, and it was at index 3. Okay, so that's find. And you can also search for strings as well. And remember, strings are between double quotes. So let's search for PLE. That starts, what's the index that the PLE starts at? Well, that's 0, 1, 2. There it is. Okay, now replace. Again, we could go to these documentation files, but these are, there it is. They get a little bit complicated. So I'm just going to show you an example of how to use the simplest kind of replace. It takes 3 arguments, a starting location, a length, and then another string. So this is the idea. s.replace start len for length, and then string s2, for example. And so what it's going to do is replace len characters from s, because s is what we're calling the replace function on. Replace len characters from s, starting at index start, and replace those characters with s2. And s2 can be as long as you ask it to be. Just whatever you give. That's how it'll work. And so this is definitely best explained with an example. So cout. Actually, how about this? S right now is apple. Let's pretend I wanted to turn it into apricot. So I just need to get rid of these last 3 characters. So starting at index 2, because that's where the second P starts, 0, 1, 2, I want to replace 3 characters with ricot. Yeah? Because if I were to replace these 3 characters with ricot, I would have apricot. You see that? That's exactly how you call this function. s.replace, starting at index 2, I want to replace 3 characters, ricot, please. And this will give back the string. But this is a special kind of function in that it also changes s itself. So s is no longer apple. It got replaced. It got updated. And so technically, you can also do this. s.replace semicolon to do the replacing. And then you can get s again. That is the new thing. So either way. So this actually changes s. Whereas some of these, like find, didn't change it. Plus didn't change it. It just gave back a new string. Size didn't change it. So there's something special about that. And then subster. This stands for substring. It's picking out a string inside of a string. So inside of apple, for example, here are some substrings. PLE, PL, app. These things. That's a substring. That's a substring. That's a substring. Any combination of consecutive characters of a certain length is a substring. So you say, so at a starting location, take some characters out of s, and how many? Take len characters out of s, okay? And make a new string for me. All right. So for example, if I wanted, I don't know, cot is a word, right? If I wanted cot out of apricot, I would have to start at what index? well, maybe pause the video and count yourself, but it's 0, 1, 2, 3, 4, so 4, index 4. And it's 3 characters long. All right, so that's exactly how you call this function again. So you have s dot substr, getting a smaller string, a substring, starting at index 4, and we want 3 characters in our extracted string. And there's our caught. And this one does not change s. So it's still apricot. Okay, yeah. Well, I think we're good to go. Yeah, these are a bit more difficult, but I just want you to have seen them before, so that when you read about them or you see them in a lab, you're not as scared. So this is how you use these things. And now that brings us to our exercises. Most of these will be optional. Just go through them on your own. Please yell at me if you have any questions or you want a hint, because they are helpful, but I won't be grading them, of course. But the first one here we'll do together. So explain the difference between 1, 2, 3 and 1, 2, 3 between quotes. So you tell me what you think. Maybe pause the video, talk to the screen. So here's 1, 2, 3, and here is 1, 2, 3. This kind of looks like a football field. That's funny. So this is a number, yes? Whereas this is a string. So it's just a bunch of characters. And this, by virtue of being a number, I can do stuff with it. I can do numbery things with it, right? I can use all these operations. I can take the power of that number, take the square root, etc. Whereas string doesn't get any of that. I mean, it gets the plus operation, but it's a different plus. But then you can also do things like, I don't know, size, substr, etc. So when you print these out, if you put them in a variable and print them out, they will look the same. They will give you back those same characters, 1, 2, 3, but the things that you can do with them, because the types are different, are completely different. Okay, so types matter a whole lot in C++, and you can actually convert between types, and I'll show you that in just a little bit. But this is where we are right now, so I hope that makes sense and that you can explain these things, like on a test, for example. Okay. So here, write a program to calculate f of 3, where f is this function here. So maybe set x to be the number 3, and then calculate all of this, which involves some roots, which you know how to do now, maybe some powers that you know how to do. Maybe to make this extra exciting, I could make it 3.5 or something. But yeah, go crazy. And then finally, write a program to get a random number between 10 and 100, convert it to a string, and then get the second digit out of it. So that's a bunch of practice with what we've been doing. So I haven't shown you how to convert an int to a string, but there is a nice handy-dandy toString function in the string library that will do that. It'll take the string that you want and give back the, it'll take the number that you want and give you back the string form of that. So yeah, that's all I wanted to say there. Good luck on these exercises, and I will see you in the next lecture.